In this lecture, we will study a fast algorithm for computing the Morse-Mail complex based on the discrete Morse theory that we studied in the previous lecture. We will begin by talking about the design of a gradient pair given a scalar function sampled at vertices. We will talk about path traversal algorithms for computing ascending descending manifolds, and finally we will discuss parallel approaches to these two steps of the algorithm, followed by an out of core computation. Central to the algorithm is the design of the discrete Morse function or gradient pairs. These two are equivalent notions. Given a discrete Morse function, the gradient field is well defined and unique. The converse is also true. We will notice that for this discrete Morse function shown on the right, the gradient pairs are oriented towards the higher dimensional cell, as we have seen in the definitions from the previous lecture. We will also notice that the gradient pairs are pointing towards the lower function values from the higher function value. So for any cell, let's consider any vertex, there is only one arc that is incident on it, which has a lower function value, and the gradient pair will be directed towards that edge. Cells that are not paired are critical. The algorithm proceeds by taking as input a scalar function f, small f, sampled at the vertices of a cell complex or a simplicial complex. So in this slide, we will see an example of a simplicial complex. In subsequent slides, we will see both examples of simplicial complexes as well as cell complexes. The algorithm works exactly the same for both cases. As a first step, the algorithm recursively extends the scalar function to all cells. Next, it computes the gradient pairs for all the cells. Finally, it traverses the gradient field that is computed, and the gradient field that's constituted by the gradient pairs computed earlier. It traverses this gradient field to compute the connections between all the critical cells. Traversing this gradient field also helps extract the geometry of the ascending and descending manifolds. So what is new in this algorithm? This algorithm provides a robust extension of the function sampled at vertices little f to capital F. It is robust in the sense that capital F capital F preserves the gradient properties of the piecewise linear function to the best extent possible. A second nice property of the algorithm is that it is parallelizable, and further, the algorithm is also amenable to out-of-core computation, where the entire data may not reside in memory. Let us begin by looking at the first step of the algorithm, namely the extension of small f to a discrete Morse function capital F. The discrete Morse function capital F at a particular cell A is A or alpha is computed as follows. Let T sub A be the highest facet of the d-dimensional cell A. And let sigma be the highest face of the cell A, which is disjoint from T sub A. Right? So sigma and T sub A are both faces or facets of A when they are disjoint from each other. And epsilon, let epsilon be any small positive real value. Let's pick an example to understand how the extension works. The discrete modes function on the vertices are directly equal to the input function little f. So f, capital F at A is equal to little f at A. Let's consider the edge AB. Capital F at AB is defined as a sum of two quantities. The first term is capital F of the highest facet of AB. The highest facet is A here. Note that the function values on the vertices are denoted by their y coordinates. So small f increases in the vertical direction. So capital F of AB is equal to capital F of A, which is the highest facet of AB, plus epsilon times f of the highest face of this AB, which is disjoint from A, namely B. Right? Now let's consider another edge, AC. F of AC is similarly defined as f of the highest facet, which is A now, plus epsilon times f of the highest face, that is disjoint from A, right? Disjoint from the highest, disjoint from T sub A. So that is C. So the second expression is epsilon times f of C. So essentially what this extension does is it takes all high dimensional cells. So let's consider AB. AB is a higher dimensional cell, and the function value assigned to AB is the higher of the two faces or facets of this cell AB. Now that's essentially what the first term does. Now the second term tries to break ties. Whenever there are multiple cells that get assigned the same function value, we would like to break the tie in order to avoid degenerate situations. And so this tie is broken by the epsilon term, which is quite small and is distinct for every cell. Let's move on to another example, which is ABC, the triangle ABC. Its highest facet is AB. So the first term is f of AB plus epsilon square times the face of ABC, which is disjoint from AB, namely C. So the second term becomes epsilon square times f of C. So note again that the first term is the term that really determines the value of the of capital F at a given cell. The second term is essentially required to break the tie. So this capital F induces a total order on the on all the faces of this particular cell ABC. So the faces of the cell ABC include AB, BC, AC, and the three vertices A, B, C. What F does is to induce a total order on all cells that that are in this list. Now this total order becomes useful, as we will see later. One final note, the epsilon is required to ensure this total order, but the actual computation of capital F at the cells need not require epsilon. The partial or the total order is sufficient to do all computations. So in practice, the function value at, for example, the triangle ABC, it's essentially equated to f of AB, and the second term is used symbolically just to break ties. So this allows the method to remain a combinatorial method rather than a numerical procedure. Let's now talk about the gradient pairing algorithm. Once small f is extended to capital F, what happens is that every cell in the cell complex becomes critical. Now, why is that true? Just a simple observation will help you convince yourself that this is actually good. So you have a vertex A and a vertex B and the edge AB. Try to convince yourself by extending small f to capital F. Try to convince yourself that this extension essentially leads to the situation where all cells are critical. So no cell is paired with another cell. So the reason is that if you pick, for example, a vertex A, then all edges that it's incident on have function values greater than it. So which means that it cannot be paired with any edge and hence remains critical. This condition is true for edges, for triangles if you have a simplicial complex, two cells if you have a cell complex, and so on. Now we begin with this apparently highly degenerate situation to start our gradient pairing. So what the gradient pairing does is essentially come up with a collection of pairs that ensures steepest descent. And the way it does this is as follows. Let's again consider that the vertical direction is the increasing direction of small f. And let's consider an edge AB. Now every cell alpha, for each cell alpha, this is how we find the pair. You choose all facets, you choose all co-facets beta, once again, choose co-facets beta for which alpha is the highest facet. Choose co-facets beta such that alpha is the highest facet, and among them you break the tie by choosing that particular beta where alpha is the lowest, where beta is the lowest cofacet. Let's look at this example. AB is my alpha, and I would like to look at all cofacets beta. First of all, I would like to look at all cofacets beta where alpha is the highest edge on their boundary. Now there could be two triangles that contain alpha, ABC and ABT. For both triangles, alpha is the highest facet on their boundary. Right? Now among the two, I want to choose that beta which is the lowest. So the lower one turns out to be the one which is incident on D. So that is beta. So this is how we break the tie for alpha. So note that and hence we pair alpha and beta. Now note that alpha and beta will be paired irrespective of which triangles you consider, whether you are currently processing ABD or whether you are currently processing ABC. This choice of alpha beta, the pair alpha beta, does not depend on which triangle you process first, because it considers the entire neighborhood. So hence the gradient pairs can actually be done independently within each triangle. So this is a lemma that is central to the speed of this algorithm. So the lemma states that all gradient pairs can be computed independent of each other. So the choice of alpha beta pair does not depend on the choice that you have made, for example, about pairing the triangle ABC. So this essentially means that every two cell can be processed in parallel by a different thread, and we are guaranteed to get the same result. Once we have the gradient pairing, computing the ascending and descending manifolds is essentially a breadth first search traversal that begins at all critical points. So the breadth first search traversal traverses through the gradient pairs, and as it traverses through the gradient pairs, it identifies the connecting critical points. So the breadth first traversal trees allow us to identify all the combinatorial connections between pairs of critical points. These combinatorial connections are essentially the one skeleton of the Morse-Mail complex, or the graph representation of the Morse-Mail complex. The breadth first search tree is typically computed using a sequential algorithm. In this case, a parallel algorithm can also be designed, and that is what is done in this particular algorithm. So the breadth first traversal is accomplished via a procedure called pointer jumping. So what pointer jumping does is, at every iteration, a node in the tree will update its parent information with the parent of its parent. So note that the breadth first search tree aims to compute from the source. It aims to compute the entire tree. And if the tree originates at a particular critical point, let's say a maximum, if it reaches some saddles, let's say saddle 1, and it reaches saddle 2 elsewhere, then we know that the maximum is connected to these two saddles in the Morse-Mail complex. Now what the parallel algorithm, the pointer jumping algorithm, does is that in every iteration, a node has a parent, and this parent information is updated to the parent of its parent. So essentially it jumps one layer up the tree. So you can quickly see that after log n iterations, every node points to the root of the tree, and hence we get all the combinatorial connections. So in other words, the pointer jumping stops when all critical points are able to find their unique pair, which is the source or the destination, as appropriate. So now that we have computed the combinatorial connections, computing the geometry is fairly straightforward. We can reuse the breadth first search tree to extract all the cells that belong to the Morse-Mail complex. So let's look at this example again from the previous lecture to illustrate this point. So we have the gradient pairs, the 0-1 pair and the 1-2 pairs, and we have the descending and the ascending and descending manifolds. In this case, we are seeing the descending manifolds, and the critical cells are the cells which have no pairs. If you start extracting the ascending and the descending cells for every critical point, then you get the combinatorial connection. So for example, extracting the ascending manifolds of the minimum or the descending manifolds of the saddle or the descending manifolds of the maximum, we get all the blue arcs, for example. So for example, these are the descending arcs or the ascending arcs, as depending on whether you are looking at the maximum as the source or the minimum as the destination. So in this case, the maximum is the source, so all the descending manifolds go towards the other cells, and similarly you can compute the manifolds for the minimum. So these give you the combinatorial connections, namely the saddle to the max and the saddle to the min. And this geometry can also be extracted from the tree. Finally, we talk about the situation where the data may no longer fit in memory. So even if the algorithm is parallelized and the performance does improve with this parallelism, often enough the data may not even fit in memory to allow for the breadth first search traversals. In this case, a divide and conquer approach helps solve the problem. So the method works as follows. Let's consider this following illustration, where we have a cell complex and a few cells that are paired with each other. We process the entire domain by breaking it into two. So the two blocks or chunks can be processed independently. However, we need to have a consistent way of handling the common boundary between the two blocks. And the way this is accomplished is by considering all gradient pairs that cross the boundary as in the following way. So if there is a gradient pair that crosses the boundary, shown using these green arrows, then the two cells that define this pair are marked critical in the two blocks as shown on the right. Now with this, we can process the two blocks independently and ignore the two green gradient pairs. and we can compute the Morse complex using the discrete Morse-based approach that we have seen in the previous slides, independently for the two blocks. And once all the ascending descending manifolds are computed, we can merge the blocks together by cancelling these exact pairs of critical cells. So the two blocks are essentially merged by cancelling this saddle max pair and this other saddle max pair. If you recall, cancelling a saddle max pair can be accomplished by reversing the V paths. So in this case, this will essentially mean introducing a gradient pair, which is the one that we had removed in the first place. So this will give us, so what we see here is the combinatorial connection for the blocks computed independently, and after the gradient pairs are reinserted, we have the combinatorial structure of the Morse-Mel complex for the entire data set. So such a divide and conquer approach can be used to compute the Morse-Mel complex for a large data set. So this algorithm needs a proof, and you can look at that in the paper. We will not discuss that in the lecture. And the lemma that is proved is that the MS complex that is computed using this divide and conquer approach does not depend on the order of cancellations. So essentially what it says is that irrespective of how you break up the data into chunks and the order in which you apply the cancellations, the output that you get will still be the same. The algorithm performs quite well in practice, as reported in the paper, for a synthetic data that is used to stress test the algorithm due to so the algorithm shows near linear scaling with size of the data. So the data is essentially a Gaussian together with a sinusoidal wave. So what this essentially does is to introduce several critical points at every crest and trough, and so hence the number of critical points also grows with the size of the data. And as you can see from the values on the right, which is the total time required to do the computation. The computation works in 5 stages, which is what is shown on the x-axis on the top. So stage 5 is after the 5th stage is complete. You can see that the runtimes increase near linearly with the size of the data. The size of the data is growing by 4 every time. The algorithm also shows near linear scaling with the number of cores. So for real world data as well, the algorithm works quite well. For example, for a 500 by 500 sized data on a Intel Xeon 4-core machine, where all the gradient pairing is done in parallel using a GTX 260 card. The algorithm takes less than half a second to compute the Morse-Mel complex. So the Morse-Mel complex can be used to identify segments such as this. So in this case, the data was from the simulation of a hurricane. A single cell from the Morse-Mel complex helped capture the eye of the cyclone and could track it over time. As you can see here, the algorithm tracks the cyclone till it enters land.